So if you're Julius Caesar and you want to send a secret message, you'd want to encode that message note so that no one else could read it. And if you're Julius Caesar, you would use the Caesarian rotation cipher, where you take each letter and you offset it by a certain number, and to substitute each letter for a different letter in the alphabet. And then you would just give the message, and then you would hope that no one else knew your rotation key, so they'd be able to decode that message. But you're not Julius Caesar, you're whoever you are here in the future, and you can actually have computers do this for you, which is nice because otherwise you'd be carving into rock and having to do each letter by hand. It'd be really tedious. So let's build a little program that can encode a message using the Caesarian rotation cipher, and we'll see how easy it is. So let's break down rotation ciphers a little bit. Here I have the alphabet with each letter numbered 1 through 26, and we're going to encode the simple phrase hello world using the rotation key of 6. So to break this down by steps, if we have hello world here in the column and we rotate each letter by 6, well, then H is the 8th letter of the alphabet. Here we go. And then we would add 6 to that. And E is the 5th letter of the alphabet. We'd add 6 to that, and so forth, going down the list. Here it is broken down again, some more. So 8 plus 6 is 14. 5 plus 6 is 11. Pretty simple addition here. It's nice. Notice that we have 29. That's a little strange. We'll look at that in a second. And here's the full thing solved. So if we have H, which is the 8th letter of the alphabet, we add 6, we get 14. And if we look at the 14th letter of the alphabet, we see that it's N. So that is the new encoded letter for H. And 5 plus 6 is 11, which is K. 12 plus 6 is 18, which is R. We repeat that again, so there's another R. And we do see here that when we have W, which is the 23rd letter of the alphabet, we add 6, we get 29. There's no 29th letter of the alphabet. So, but we do know that C, because I've done this before. But here's how that works. If you pretend that the alphabet actually repeats and it keeps going here, so we get A, B, and C, then A would be the 27th letter, B would be the 28th letter, and C would be the 29th letter. So C is the 29th, but it's also the 3rd. And if we do a little bit of simple arithmetic, 29 minus 26 is 3. So, and if you get to a number that's larger than 26, you just have to offset it by the length of the alphabet, and then you'll get the letter that you really need. It's for rotating around the alphabet. So that's basically the problem. We just need to do this simple translation algorithm for every single letter. And the algorithm is broke down into 3 steps. There's convert letter to number, and we can call that an encoding step. And then you add the rotation key to that number, and that's just addition, so there's already a block for that. And then finally you convert the number back to the letter, and we'll call that decoding for now. So we just have to do these 3 steps for every single letter, so you know if you're doing the same thing for every letter or every element of a list, you know you're going to be using a loop. So we'll do that in a moment. So here's a brand new Snap project, and let's do each of those steps one at a time. Let's build a custom block for encoding. We'll call it encode letter, and it will be a reporter block because it's going to give us back a value that we'll use later. And letter will be an input. We'll pass in a letter and we'll expect to get back a number. So if we show that down here, we now have this block called encode, and what we want to happen if we enter A, it'll say 1, B, it'll say 2. Of course, it's not doing that yet, so let's build that code. A naive way to do this would be to use 26 if statements and say if letter is equal to A, report 1, and if letter is equal to B, report 2. But that's kind of obnoxious to do. We should let the computer do the work for us. And we've already done these 3 steps in the input validation, where we create an alphabet list. So I'm just going to repeat that really quickly. So alphabet will first be equal to the string A, B, C, D. So that's the whole alphabet. And then we're going to turn it into a list by overriding that variable and using split word by letter. All right. And let's just test to make sure that I typed everything correctly by just saying the alphabet list. So if we were to encode B, it would say a list, and it has 26 elements, and they start at A and end at Z. So I think we got that right. So we get rid of this say block. So what do we do in order to convert this letter into a number? Well, if we were to iterate over the list, we start at 1 and then we count forward, we'll have a number for every letter in the alphabet. And we can check to see which letter of the alphabet is equal to the letter that was passed in, and then we'd have a number there. So I'm just going to show a list, a loop over a list, like we've been doing for a couple weeks now. We'll have a repeat loop, and we know that it repeats 26 times because that's the length of the alphabet. And we know that we'll increment counter by 1 each time we go around the loop. So the first time we go through the loop, counter will be 1. The second time we go through the loop, counter will be 2. And we want to get each letter for each counter value of counter inside the alphabet. And we can actually just make it in test say each of those letters to make sure that our loop is working correctly. We'll make it say them quickly, even quicker than that actually. So if we run this, it says A, B, C, D, and I'll go through each letter in the alphabet. At some point, when the letter variable here that was input is equal to one of those letters, we can stop counting because we found what we wanted and we can just return counter. In fact, just to show that we have both variables, let's just put a little test script in here and say this letter is the letter of the alphabet, and say counter here, apply. So that's kind of a long line of code here. But if we run it, let's say, we said H is the 8th letter of the alphabet, and it's just counting all the way through. So we have a nice alignment between the counter variable and the letter we're using there. If we want to see that our letter input is equal to the letter that we're using in the loop at that point, we can use equality and check, does letter equal item counter of the alphabet? If it does, let's just report counter. So if we say, let's apply this, smaller, if we say encode B, it says 2. If we say encode T, it says 20. And one thing to do here, if we were to encode 5, it would say, oh, this didn't report, something went wrong. So I'm just to make sure everything keeps working, I'm just going to put a report here at the end, which it wouldn't get to if it found a letter inside this repeat loop, it would report early. But if it didn't find a letter, it would finish all 26 iterations and it would get down to here. Let's just report -1 for now. So code 5, -1, that just kind of means we didn't find it. So F would be 6. All right, that's step number 1. Let's build a block for doing the opposite. Let's take a number and turn it into a letter. So let's try decode number. Also a reporter block. These are very similar, they're just the opposite. Number will be an input, and it will be specifically a number, which makes it have a round input, and you can't type letters in there. You type 1, but you can't type A. So how do we get the number for the letter for a number? Well, let's just do start the same way. It's the same process, so we can start with the same starting point and get our whole script here. But we don't need all this stuff. We don't need to repeat through a bunch of stuff. Because if we have a list that's the alphabet, and we want to get a letter at the 8th position, we can use item 8, and it would give us back H. So we don't even need this counter variable. So this gets really easy, actually. We just take number, item number of alphabet, then we get a really easy conversion between numbers and letters. Let's see if that works. So if we take, what do we say, 8 is H. A, oops. Oh, sorry, 1 is A, and 26 is Z. So now we have back and forth conversion. In fact, you can kind of like put these back and forth for real. Say, take F, encode it to a number, then take that number and encode it back into a letter. You should get the same thing. So we take R and encode it to a number. R would give us 18. We put 18 inside here. It gives us back R. So these are, I suppose, transitive operations. So that's the heavy lifting involved in converting a message. So let's build a little program that uses these. We'll have it start on green flag, and we'll first have it ask, what is the message you want encoded? So what message, or enter your message. And I'm going to save a script variable called message, and I'm going to assign the answer to that. So now message will be whatever you type in. Then I'm going to ask the second question. What is your rotation key? And so I'll have another variable called key, and I'll assign the answer to that. So now I have two variables that I can use to convert your message using the rotation key. So a message is some text, and text is a bunch of letters strung together. And we can loop over each letter using a simple list loop and get each letter and perform those three operations. So let's do them one at a time. To make a list loop, we need a counter variable and we need our repeat. How many times do we repeat? Well, message has a certain length to it, and we can get that length using the operator here. And so we can repeat that number of times, and we can change counter by 1. So let's make sure that that's working correctly. So if I say counter for a brief period of time, and I enter hello as my message, and then ask me for rotation key, then it'll count 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4, 5. There's only 5 letters in hello. All right, so that's a start. So now we want to get each letter, and we can use the letter 1 of word for that. So if we take our message and we use the counter variable to increment which letter we're getting each time, we should now be able to print out each letter individually. So hello, put in a key, it says H-E-L-L-O. There we go. So now we have the first step of our encoding algorithm. So we can encode that letter, and if we do H-E-L-L-O, it should print out a bunch of numbers instead of letters. And we can look at what our letters should be. If we look here, they should be 8, 5, 12, 12, 15. So let's see if this works. We put in 6, 8, 5, 12, 12, 15. There we go. So now that we've gotten the first pass of letters, so we've converted H into 8, we want to add 6 to that. And we can use the addition operator for that, obviously. So if we take the encoded letter, so it's a number now, and we add key to it, we will get the encoded numbers. So HELLO, rotate 6, 14, 11, 18, 18, and 21. Does that work? 14, 11, 18, 18, and 21. Perfect. So finally, we want to decode those letters back into numbers. There'll be different numbers than we started with. So this is really the whole algorithm right here. Let's make sure it works. What are we expecting to get? We want to get NKRRU. All right, let's see if this works. Hello, encoded with a rotation key of 6 is NKRRU. Great. And because we don't want it to print out one at a time, we're actually going to add one more variable, which will be the encoded message. We're going to set it to a list. And instead of saying each encoded letter, we're going to add each encoded letter to our new message list, our encoded message list. Get rid of that. And then what we want to do at the end is just say the encoded message join together. So join has a nice little functionality here where we say encoded message and join will put it all into one string. So let's do hello, encoded 6, NKRRU. There we go. Of course, we should test it with our full phrase, hello world, and encode that by 6. And we see it's NKRRUUXRI, which doesn't look right. I think that's actually XRJ. That's just Snap being weird again. But we're missing our C, NKRRUCUXRJ. So why do we were missing a C? Well, C was kind of special, remember? C, W converts to C, and W is the 23rd letter of the alphabet, and we're rotating by 6. It means we're getting 29. We have to subtract 26 in order to get to 3 so we can get C. So it's printing out nothing there, and that's a bug in our program. So what do we want to do about this? Well, I think we can just make it so decode is allowed to take numbers larger than 26. If the number is larger than 26, we want to subtract 26 and then use it. So if it's 29, we subtract 26, now it's 3, and now we get C. So we can do that with an if statement and the greater than operator and say, is the number greater than 26? If it's greater than 26, we want to subtract 26. So we'll change number, change number by negative 26. Hit apply. Try this again. Hello world, rotate 6. There we go. NKRRUCUXRJ. That's pretty great. And what's cool about this is that we can use this to decode messages as well. All you need to do is pass in a negative rotation key. Because if it was encoded with 6, all you need to do is decode it with negative 6. If you take in, which is 14, and you subtract 6, you'll get 8. So let's give that a shot. If our message is NKRRUCUXRJ, and we enter negative 6 for a rotation key. Oh, it almost worked. We have that missing W again. I think this is a D, and it's also getting cut off because of Snap. But it's hello world, but the W is missing. Why is that? Well, again, we're doing this backwards, right? We're taking a C, which is 3. We're subtracting 6, and then we should get W. But 3 minus 6 is negative 3. There's no negative third letter of the alphabet. So we need to do the same thing but backwards. If you take negative 3 and you add 26, you'll get 23. So we need to change our decode block again one more time to do a check to see if number is less than less than 1, and then we add 26. So if we do number is less than 1, then we change number by 26. Apply. Okay. NKRUCUXRJ, encoded with -6 or decoded with -6 is hello world. Again, that's a D. Snap's being weird. So that is how you can write a script that takes a message or a key and encodes it to carry a secret message. And if you'll notice, there's actually a short delay here, right? If I type in hello world and 6, it takes a brief moment for it to print out. And some of you have learned about the warp block. This is a perfect example for warping. What Snap does in between each block here, and this includes all the blocks that are inside the custom blocks, is it pauses for a brief moment to see if it needs to draw to the screen. And there's no drawing happening here, it's all just computation. So if we put warp around it, it stops those pauses and does this as fast as possible. This will now get really fast. If I hit 6, and then bam, instantaneous. It's really easy for a computer to do this, which is why encryption has gotten a little more complicated since the days of Caesar, because if you were given a message and you knew it was a Caesarian cipher and you didn't know which number it was, you could just make a loop that just went through all 26 possibilities, and the computer could do it nearly instantaneously, and you could just look at which one actually made sense, and then you would know what the message was. So this is a pretty good start, and what I would love for people to do is take this and figure out how to do a Veneer cipher, which was also listed in the Blend2Bits book. Veneer cipher is a little different than a rotation cipher, but it uses the same principle in that if you had the phrase hello world, you want to rotate it across another phrase. This is called the key phrase. And instead of having a letter, you're going to a number that you rotate it, you're going to use the number that corresponds to each letter of the phrase. So if you have the phrase cat, which is C is 3, A is 1, and T is 20, then you're going to rotate your encoded message by each of those letters. So it says H rotates C, E rotate A, L rotate T, L rotates C. And you're going to continue to repeat cat as far as long as you need to. And so that breaks down very similarly, where you're going to take H, which is 8, and add C, which is 3, and E, which is 5, and A, which is 1, and you're going to, so that it changes what you rotate by for every single letter. And you end up with something kind of similar. The math ends up being the same, and you have to do the repeating around the alphabet the same way, because L is 12 and T is 20, so you get 32 when there's no 32nd letter of the alphabet, so you have to do 26, which might subtract 26, which gives you 6, and then you get F. And it's the same process, it's just one extra step of complication. So that's the assignment. Take what you've learned here, and instead of rotating it by a single letter key, a number key, you're going to rotate it by a word, and you're going to have to take each letter of the word and find out what rotation key to use there. So give that a shot.